When selecting the overcurrent protection device, opt for the primary side of a transformer. It is essential to base the calculation on the actual input voltage rather than relying solely on the nameplate voltage. In this scenario, a 30 kVA three-phase transformer is being installed to feed a printing press. The press requires a 230 volts supply, and the transformer is intended to convert the existing delta feed to a Y configuration. While there may not be a direct neutral connection to the press, the delta to Y transformation serves other purposes, such as providing a more stable voltage and potentially reducing harmonics. The existing setup includes a 235 volts input voltage. An initial 100 amps opt feeds the primary side, and the secondary side connects to a service-rated disconnect equipped with 100 amps fuses. This disconnect then feeds a 125 amps rated subpole, which further distributes power through a 3-pole 50 amps breaker and a 2-pole 30 amps breaker to the printing press. The full load amperage, or flow, of the press is approximately 73 amps when considering a 125% factor. Using the nameplate voltage of 240 volts, the calculation suggests a primary opt size of 90 amps. However, when the actual input voltage of 235 volts is used, the calculation results in approximately 92 amps. According to the National Electrical Code, specifically Section 90.3, it is permissible to use the next highest standard opt size. Therefore, a 100 amps opt can be used. The crucial point here is to prioritize the actual input voltage in the calculation. The inspector should not require a downsizing of the primary opt to 90 amps because the actual input voltage necessitates a larger opt. The opt is designed to protect the transformer from overloads and short circuits. Firstly, it is designed to protect the primary windings from excessive current draw. Secondly, the opt prevents damage to the transformer in the event of a fault on the secondary side. Thirdly, selecting the correct opt size ensures compliance with the National Electrical Code, specifically Article 450, which covers transformers. To accurately determine the appropriate opt size, the following steps should be taken. 1. Obtain the transformer's nameplate information, including the kVA rating, primary voltage, and secondary voltage. 2. Determine the actual input voltage at the transformer's location. This can be measured using a voltmeter. 3. Calculate the primary current using the formula I equals kVA times 1000 divided by the square root of 3 times the primary voltage. 4. Multiply the primary current by 1.25 as per the National Electrical Code to account for continuous loads. 5. Select the next higher standard opt size based on the calculated current. Remember that overcurrent protection is based on both overload and short circuit protection, while grounding provides a safe path for fault currents. Proper grounding is essential for the safe and reliable operation of any electrical system. The grounding system ensures that fault currents have a low impedance path back to the source, which helps to quickly trip the overcurrent protection devices and prevent electrical shock hazards. The size of the grounding conductors must be adequate to handle the maximum fault current that could occur. The National Electrical Code specifies the minimum size of grounding conductors based on the size of the overcurrent protection device. The grounding electrode system typically consists of a ground rod, a metal water pipe, or a concrete encased electrode. The grounding electrode provides a connection to the earth, which helps to stabilize the voltage and provide a reference point for the electrical system. The resistance of the grounding electrode should be as low as possible, and it should be tested regularly to ensure its effectiveness. Bonding is the process of connecting all metal parts of the electrical system together to create a low impedance path for fault currents. This includes metal conduits, enclosures, and equipment frames. Bonding helps to equalize the voltage between different metal parts, which reduces the risk of electrical shock. The bonding conductors must be sized appropriately to handle the maximum fault current that could occur. Surge protection devices, or SPDs, are designed to protect electrical equipment from voltage surges caused by lightning, utility switching, or other transient events. SPD divert the surge current to ground, preventing it from damaging sensitive electronic components. SPD are typically installed at the service entrance and at various points throughout the electrical system. The selection of SPD should be based on the voltage and current rating of the electrical system, as well as the level of surge protection required. Regular inspection and maintenance of electrical equipment are essential for ensuring its safe and reliable operation. This includes visual inspections, testing, and cleaning. Visual inspections should be performed regularly to identify any signs of damage, such as cracked insulation, loose connections, or corrosion. Testing should be performed to verify the proper operation of overcurrent protection devices, grounding systems, and other electrical components. Cleaning should be performed to remove dust, dirt, and other contaminants that can affect the performance of electrical equipment. When performing any electrical work, it is important to follow all safety precautions to prevent electrical shock and other hazards. This includes wearing appropriate personal protective equipment such as gloves and safety glasses. Always de-energize the circuit before working on it and use a voltage tester to verify that the circuit is de-energized. Never work on electrical equipment in wet or damp conditions. If you are not qualified to perform electrical work, hire a licensed electrician to do the job. Furthermore, consider the impact of harmonics on the electrical system. Harmonics are caused by nonlinear loads such as electronic devices and variable frequency drives, and can lead to overheating of transformers, increased energy losses, and reduced equipment life. To mitigate the effects of harmonics, consider using harmonic filters or line reactors. These devices help to reduce the harmonic currents and voltages, improving the power quality of the electrical system. Power factor correction is another important aspect of electrical system design and operation. Power factor is the ratio of real power to apparent power, and it indicates how efficiently electrical energy is being used. A low power factor can result in increased energy costs, reduced system capacity, and voltage drop. Power factor correction can be achieved by installing capacitors or other power factor correction equipment. These devices help to reduce the reactive power and improve the power factor, resulting in a more efficient and reliable electrical system. Load calculations are essential for determining the appropriate size of electrical equipment, such as transformers, conductors, and overcurrent protection devices. Load calculations involve estimating the total amount of power that will be consumed by the electrical system. The National Electrical Code provides guidelines for performing load calculations based on the type of load and the expected usage. Accurate load calculations are essential for ensuring that the electrical system is adequately sized and can handle the expected load without overloading or overheating. The selection of conductor should be based on the ampacity of the conductor, which is the maximum amount of current that the conductor can safely carry. The National Electrical Code provides tables that list the ampacity of conductors based on their size, insulation type, and installation method. It is important to select conductors that are appropriately sized for the expected load and the environmental conditions. The use of appropriate wiring methods is essential for ensuring the safety and reliability of the electrical system. The National Electrical Code specifies the approved wiring methods for different types of installations. Wiring methods include conduit, cable, and open wiring. The selection of the appropriate wiring method should be based on the environmental conditions, the type of load, and the applicable codes and standards. Ground fault protection is designed to protect people from electrical shock hazards caused by ground faults. A ground fault occurs when current flows through an unintended path to ground, such as through a person's body. Ground fault protection devices, such as ground fault circuit interrupters, or GFCIs, and ground fault equipment protection, or GFEP, are designed to detect ground faults and quickly interrupt the circuit, preventing electrical shock. GFCIs are typically used in residential and commercial applications, while GFEP is typically used in industrial applications. Short-circuit current ratings are essential for ensuring the safety of electrical equipment in the event of a short circuit. A short circuit occurs when there is a low impedance path between two conductors, resulting in a large flow of current. Electrical equipment must have a short circuit current rating that is equal to or greater than the available fault current at the point of installation. This ensures that the equipment can safely withstand the forces and heat generated by a short circuit without failing or causing a fire. Regular maintenance of the transformer, including inspection of the windings, bushings, and cooling system, is crucial for preventing failures and extending its lifespan. Also, consider ambient temperature when selecting components. High ambient temperatures can reduce the ampacity of conductors and the capacity of electrical equipment. The National Electrical Code provides correction factors for adjusting the ampacity of conductors based on the ambient temperature. It is important to select equipment that is rated for the expected ambient temperature to ensure its safe and reliable operation. Coordination studies are used to ensure that overcurrent protection devices are properly coordinated to minimize the extent of an outage in the event of a fault. A coordination study involves analyzing the time current characteristics of the overcurrent protection devices to ensure that the device closest to the fault will trip first, while minimizing the impact on the rest of the electrical system. This study should be performed by a qualified electrical engineer. Proper labeling of electrical equipment is essential for ensuring safety and facilitating maintenance. Electrical equipment should be labeled with its voltage, current, and power ratings, as well as any other relevant information. The label should be clear, legible, and durable. Additionally, consider the future expansion of the electrical system. It is important to design the electrical system with enough capacity to accommodate future loads. This may involve installing larger conductors, transformers, and overcurrent protection devices than are currently required. Planning for future expansion can save time and money in the long run. I never underestimate the importance of documentation. Maintaining accurate and up-to-date documentation of the electrical system is essential for troubleshooting, maintenance, and future modifications. The documentation should include single-line diagrams, panel schedules, equipment specifications, and wiring diagrams. This ensures that the transformer operates within its design parameters and prevents premature failure.